Hello everyone. On this video we will be going over the arc length and polar coordinates. Okay, so starting off we will see exactly how we come up with the formula that we're going to use. Alright, so first we're going to let r equal some f of theta, and pick a randomly curved shape. Okay, so it doesn't matter which randomly curved shape you use. So we're just going to use that shape. Okay. Now with this shape, or any shape whatsoever, if you zoom in very closely, we'll have a little area there. That length there we'll call df. Okay, and around this entire shape, just a collection of straight lines that are all, we'll just call the length of s. Okay, so if we get all of those values and we add all of those lengths of s together, we'll see that the length is equal to the integral of ds. Basically adding all of those ds values together. Okay. So from there, what we're going to do is we're going to pick one of them. So let's say if we pick that one in and we zoom in really almost close to infinitely tight. If you zoom in close enough, even on a curve, that ds will look like a straight line. Okay? Now for that ds, remember this is your x-axis. So this down here is going to be your length of x. And let me kind of darken that up a little bit. And this is going to be your length of y. So if we use the Pythagorean theorem, we know that dx squared plus dy squared equals your ds squared. Or if we square root both sides, that gives us ds equals the square root of dx squared plus dy squared. We kind of simplified a little bit. Okay, so where do we go from here? Glad you asked. If you remember at your parametric curve, x equals r cosine theta and y equals r sine of theta, you can also write that as x equals f of theta cosine theta and y equals f of theta sine of theta. Okay. This side is actually a little bit easier on our proof, so we're going to use that. Okay, so first thing we're going to see is that we find the derivative of both of those. Dx d theta, actually just solving for dx because we're going to use differentials. Using differentials definition from Calc 1, I believe it is. Dx is equal to f prime of theta cosine theta minus f of theta sine of theta with respect to theta. then dy is equal to f prime sine of theta. Okay, so f prime of theta sine of theta plus f of theta cosine of theta with respect to theta. Okay, so now the next thing we're going to do is we're going to square all of these. So if we square this side, square this side, square this side, square this side. Okay, so we're running out of space here. So what we're going to do is we're going to continue this on the next page. So if you are still writing, feel free to press pause. But we're going to go ahead and move on to the next page of our proof. Okay, so if we add together our dx squared plus dy squared, that is going to equal if we got our dx squared, just going back to the previous page, we have our dx squared, we're squaring this side, and we're just using the FOIL method. Okay, so that's f prime of theta squared cosine squared theta minus 2 f prime of theta f of theta cosine theta sine theta plus f of theta squared sine squared theta and our d theta is squared. Okay, same thing with our dy squared. We'll end up with f prime of theta squared sine squared theta plus 2 f prime of theta f of theta cosine theta sine theta plus f of theta squared cosine squared theta, and again we have our d theta squared. So if we go ahead and add these two together, dx squared plus dy squared, we're just adding these two sides together. So if we have our f prime squared cosine squared and we add it to f prime squared sine of squared, we can actually factor out the f prime of theta squared. Okay, so we end up with f prime of theta squared cosine squared theta plus sine squared theta. You notice here, minus 2 f prime f cosine sine plus 2 f prime f cosine sine. So these two, when you add them together, will actually cancel each other out. Okay, so we go ahead and we add together our two sections there. So plus f of theta squared. So we go ahead and factor out of both of those. So we have sine squared theta plus cosine squared theta. And you can see here that d theta squared is already factored out from both of these. or d theta squared. Okay. So that means we remember that ds is equal to the square root of dx squared plus dy squared. Okay. So if you notice, when we add these two together, that gives us the square root. But before we do that, you notice that cosine squared plus sine squared both equals 1. So we can actually get rid of those because it's just 1 times each of those, which leaves us with f prime of theta squared plus f of theta squared times d theta squared. Okay. So actually what we can do is we can separate this and the d theta squared. So that means ds equals the square root of f prime of theta squared plus f of theta squared times the square root of d theta squared. Well, should be. Doesn't matter if it's on the outside, but just to keep up. I'll put the square root here and d theta squared. There we go, just to keep up with the previous. Okay, so if we go ahead and separate that, we see that the square root of d theta squared, because the exponent and index cancels out, is just d theta. Okay, so ds is equal to the square root, move that up a little bit, f prime of theta squared plus f of theta squared with respect to theta. So if we go ahead and integrate both sides, integral and derivative both cancels out. So we see that s is equal to the integral between two values, because remember on our first page this was between our two values that we're going to find the length. So we'll say those values are a and b. The square root of f prime of theta squared plus f theta squared with respect to theta. Or if you want to simplify that even more, s can be equal to the integral from a to b, the square root, instead of f prime, since r equals f of theta, and dr d theta equals f prime of theta, we can just replace those. So instead of f prime of theta, we can make that dr d theta squared plus r squared with respect to theta. So really you can use either formula to find our arc length. Arc length of polar coordinates. Alright, so move that up a little bit. So if you are still writing, feel free to press pause, but we're going to go ahead and start with our first example. Alright, so for example, what if we wanted to find the length of the arc from theta equals 0 to theta equals 2 pi for the cardioid, VIOD, R equals 2 minus 2 cosine theta. Or if you wanted to write, you can write as R equals F of theta equals 2 minus 2 cosine theta. Alright, so to solve this one, we can see that the formula for arc length is S equals the integral from A to B of the square root of F of theta squared plus F prime of theta squared with respect to theta. Or you can use R if you like. So that just means this will equal the integral from 0 to 2 pi of the square root of F of theta squared. So remember that your R is just your F of theta. Okay, so that will be 2 minus 2 cosine theta squared. Oh, gotta make that a little longer. Plus F prime of theta, so our derivative of that will end up being 2 sine theta. So F prime of theta will be 2 sine theta squared with respect to theta. Alright, so if we go ahead and we simplify that a little bit more, if we go ahead and factor this out and use the FOIL method, we end up with the square root of 4 minus 8 cosine theta plus 4 cosine squared theta. And we have our 2 sine theta squared. That will end up with plus 4 sine squared theta. And that's with respect to theta. Alright, so if we kind of look at these two, we can factor out a 4. So we have the square root of 4 minus 8 cosine theta plus 4 cosine squared theta plus sine squared theta with respect to theta. Okay, so you remember cosine squared plus sine squared is equal to 1. Okay, so we end up with 4 plus 4, because this is just 4 times 1 is 4. So we end up with, from 0 to 2 pi, the square root of 8 minus 8 cosine theta. Made that one too long. With respect to theta, which equals the integral from 0 to 2 pi. If we factor out an 8 here, okay, we can factor out the 8, so we have our square root of 8 times the square root of 1 minus cosine of theta with respect to theta. Alright, so we can see that if we, using our trig identities, so if we use the trig identity, sine squared theta equals 1 minus cosine 2 theta all over 2. That will give us our square root of 8. We can actually simplify that. So from 0 to 2 pi, you can move that out a little bit. So square root of 8, that's actually 2 square root of 2. Okay. So we now have 2 sine squared theta over 2 with respect to theta. Okay, so we can actually simplify that. So if we get that square root of 2 and we factor this out, so we have square root of 2 times square root of 2 is 2, so 2 times 2 would be 4. So that would be 4 times the integral from 0 to 2 pi. Sine squared theta over 2, and the square root of that, the square and the square root cancels out, so we just have sine of theta over 2 d theta. Clean that up a little bit. Alright, so from there we just go ahead and simplify using U substitution. So let me simplify that using U substitution. If U equals theta over 2, let me move that down a little bit, then 2 du equals d theta. Alright, so we end up with 8 times negative cosine of theta over 2 as our integral. And that's from 0 to 2 pi. Okay, so if we plug in our 2 pi, 8 times, negative cosine of 2 pi over 2 is just negative cosine of pi, which is negative 1, so we have 1, plus cosine of 0, or negative cosine of 0, is 1. Basically, we end up with 1 plus 1, or 8 times 2, which is 16. Okay. Alright, so looking at that, we are all done here. So hopefully this has made sense, and I will see you on the next video.